In this second unit of our class, we talked about descriptive statistics in Chapter 3, and we're going to talk about relationships between two numerical variables here a little bit in Chapter 10, talking about correlation and regression. Although Chapter 10 in our textbook has 5 sections, we're only going to cover the first 2, the Section 10.1 on correlation and Section 10.2 on regression. First, we introduce the concept of the linear correlation coefficient, which we will label with a lowercase letter r. We're going to see that r is a number that measures how well paired sample data fit a straight line pattern when we graph the data. We will use data coming from samples where there is an x value paired with a y value. We're going to find the calculation for r and then use that number to decide whether we have enough evidence that there is a linear relationship between x and y. In this course, we consider only linear relationships, although there are many other interesting relationships that are possible: quadratic relationships, cubic, other nonlinear patterns. But for the purposes of this elementary statistics class, our focus will be on linear relationships between x and y. In general, we say that a correlation exists between two variables when the values of one variable are somehow associated with the values of the other. And so correlation is synonymous with relationship. If there's a relationship between x and y, we say that there is a correlation. So we're going to elevate our language just a little bit. We are going to be talking about linear correlation. So linear correlation assumes that there is a relationship between x and y, but that relationship is linear in nature. We're going to be looking at paired data that will be graphed, very similar to how you would graph ordered pairs in an algebra class, and then we're going to see how well those points form a pattern. In order for us to look at paired data, we use a graph called a scatter plot, which we introduced in Unit 1 of our course. A scatter plot is simply a collection of ordered pairs that have been plotted. In this chapter, the ordered pairs are coming from paired data. So think, for example, of us taking the height measurements and the weight measurements for 30 individuals, for instance. Each individual is going to have a height and a weight, and so that person's height can be thought of as the x variable, that person's weight could be thought of as the y value, and the reason we say that the data is paired is because both measurements are coming from the same individual. So then those x and y ordered pairs are graphed, and this is an example of what a scatter plot could look like for paired data. In this particular example, we see that the ordered pairs don't line up perfectly. There is some scattering about. However, if we were to take a step back and kind of look at it as if it was a piece of art and maybe squinted our eyes a little bit, I think we would agree that overall we do see somewhat of a linear pattern, almost like a thick marker going from the bottom left corner of our graph to the top right corner of the graph. So while it's not perfectly linear, there is a very strong pattern here, and we do say that overall it does have a linear trend. This is another scatter plot, and unlike the previous one, the line that we can make out has negative slope. It's decreasing in y value as we increase the x value. So again, it's not a perfectly linear graph. However, the scattering is a little bit less in this particular graph. We see that the ordered pairs are almost clustering a little bit better, and we have to use less of a thick marker to imagine the linear trend happening here. So between this scatter plot and the one we saw in the previous slide, I would say that this certainly is a stronger linear relationship between our x and the y variables. The one in the previous slide certainly was visibly linear, but this one is more condensed. Here's a scatter plot where, squint as we may, step back as far as we want, it's going to be nearly impossible to make out a linear trend. So a good non-example of a linear relationship here in this example. In fact, not only do we not see a linear trend, but I don't think we see any type of trend at all. So in this case, we would say that there is no linear correlation. This example is pretty interesting because I think we would agree that there is not a linear pattern. After all, where would it start? Where would it end? Is it going from the bottom right to the, from the bottom left to the top right, or is it going from the middle top to the bottom right? While we don't see a linear trend, we certainly do see a very strong presence of a trend. It just happens to be curved, almost as if it were quadratic in nature. So we need to be careful with our language. Just because we do not have evidence of linear correlation doesn't necessarily mean that there's no correlation whatsoever. Remember, correlation on its own means relationship, and clearly in this example there is a relationship between x and y. It just happens to not be linear. Here's the collection of the 4 scatter plots that we saw just a moment ago. I want to point out that when our linear pattern is increasing in y values as we go from left to right, so in other words, as the x values increase, the y values are increasing as well, we say that this linear pattern has positive linear correlation. And when we see the opposing trend where our x values are increasing from left to right, but the y values are decreasing, so that the line seems to be falling, we say that there is negative linear correlation. And then of course in the last 2 scatter plots here, in both cases we would say that there's no linear correlation. However, in this case there's no correlation at all because there doesn't seem any relationship between x and y present. This scatter plot, however, no linear correlation, but certainly signs that there is a correlation of some other type. Now let's return to this number called lowercase r. This is our linear correlation coefficient, and it is used to measure the strength of linear correlation, the strength of that linear relationship between numerical x values and y values from a sample. This linear correlation coefficient r is a single number, and it is computed either by using some manual formulas, and we'll go through those formulas in the coming slides, but however we are going to be finding r using our calculators, either the Texas Instruments 83 or 84 models, and I will post a separate video on YouTube as to how to use the calculator to find r. Let's talk about the properties of the linear correlation coefficient. First of all, r is always a single value between -1 and 1 inclusively. So r can take on a value of exactly -1, and it can take on a value of exactly +1, and of course any value in between. If all the values of either the x variable or the y variable are converted to a different scale, r doesn't change. So for example, if we were comparing the heights and weights of individuals, and the original heights were in centimeters, and we converted all those to inches, and let's say the original weights were all in kilograms and we converted to pounds, changing those measurement scales would not change the calculation of r. In addition, r is not affected by whether one variable is called the x variable and the other one is called y. They actually could be interchanged. So if we had started out treating heights as x values and weights as y values, and we calculated r, switching the two around and calling weight x and height y would not change the result of that r calculation. R, as we said earlier, measures the strength of that linear relationship, and it also can tell us if we do not believe that there is a linear relationship at all, but it won't tell us what the nature of any other possible relationship would be. So if you think of that fourth scatter plot where we had kind of that curve, kind of the cup opening downward, we probably would get an R value very telling that says that we don't think there's linear correlation, but an absence of linear correlation doesn't tell us very much about what other kinds of relationships may be present. And finally, R is very, very sensitive to outliers. It is not resistant, and therefore any presence of outliers, which are those extremely low or extremely high values, could have a great impact on the result of that calculation of R. So now we're going to jump into how to calculate R, and the calculation of R is going to be rather tedious when you use the manual formulas. However, we're going to review the formula because we want to see what is actually feeding into that calculation to help us interpret those results. So there's lots of notation here to review if you're looking at the formula. Remember that this E looking symbol is a Greek letter. It's the capital letter sigma, which in mathematics designates sum or addition. So these are just some of the quantities that feed into that manual calculation of R. Here are some others. I want to point this out. It's not going to be very relevant until we get to Chapter 8 later in our course, but in our first unit we did spend some time talking about the difference between data that comes from a sample and data that comes from a population. R is a sample statistic. It's a number that is calculated from sample data. Rho, which is this funny P looking symbol, is a Greek letter. It's actually the Greek letter R, and that is a symbol that we use if we're calculating the linear coefficient, the linear correlation coefficient for an entire population, so using census data. So R is a sample statistic, Rho is a population parameter. In this chapter, we're only going to be looking at sample data, so we're only going to be using the lowercase r label. Before calculating R, especially because it is tedious, it's important to make sure that certain requirements are met. First and foremost, we need to start with good data. So we want to make sure that our data is paired, that we have two numerical variables, and that the data is coming from a simple random sample. We talked about all the different ways that data could be biased or not representative if we use a less strict sampling method. Secondly, we want to make sure that if we were to look at the ordered pairs in the scatter plot, that we believe that there is some sort of linear pattern. If we see a scatter plot that shows no linear trend whatsoever, calculating R will be rather pointless. So we want to at least have the suspicion that there is a linear trend. And finally, we want to be cautious about any outliers present in the data. So if we see any extreme values, we want to kind of check them out, see if they are legitimate, and maybe calculate R with and then without them to see what that impact is on the R calculation. Now here is that very, very lovely formula for calculating R manually. It is a lot of work, especially if you have a lot of data values in your sample. Maybe not super tedious if you had, say, 10 values, but in the real world, we rarely have sample sizes that are that small. We usually have many, many more values. So certainly not a formula that we want to use often, because there are lots of places that we can make a computational error. It does say it's a good format for calculating R, but again, still very, very tedious work. If we were to use the formula, we would want to round the linear correlation coefficient R to 3 decimal places to compare it to some values on a table that we'll see in just a bit. Again, we will be using our calculator to find R, so we will be given a 3 decimal value using technology. Let's look at the following example, and we are going to find R with technology. Again, we're going to show the process of using the calculator on a separate video, but here's what we have. It says that we have Powerball jackpot amounts and then the number of tickets that were sold for each one. So this is paired data. So each one of these columns is an XY ordered pair. This is the ordered pair 334, 54. This is the ordered pair 127, 16, and so on. So we see that there are 9 pairs of data, 9 ordered pairs. If we run technology, whether it be with a computer or with a calculator, we get different views, but they all come up with the same result. So here are some of the outputs by different technology, and the one that I want to focus on is this one right here, because that is what our calculator is going to show us. And again, we'll show you in a separate video how to get to this, but here is that R value, and if we round to 3 decimal places, we find that R is approximately 0.947. So if R is equal to 0.947, what does that mean in terms of whether we have evidence of a linear trend? Well, we didn't look at the graph just yet. We will in a future slide. But what we will see in that scatter plot is that this data actually does follow a very clear linear pattern, and the slope of that line, of that linear trend, is positive. So it's rising as we move from left to right. Now, there's a way for us to test whether we have evidence of linear correlation or not, because it's not a gray area as to some people saying they have enough evidence, others saying not so much. So we're all going to use the same standard to decide if we have evidence that there is a linear trend, and we're going to be using a significance level of 0.05. For now, just kind of take it as I say it. We're going to be talking about significance levels much more in Unit 5 of this course when we get to Chapter 8 and hypothesis testing. For now, just see it as related to the discussion we had earlier in this unit about values that are significant and values that are not significant. So here is the scatter plot for those 9 ordered pairs. And again, I promised you that we would see a linear trend, and here it is. You can see that if we were to trace over this with a nice thick line, it would have a positive slope, and we really don't have to squint that hard to be able to make out that upward linear pattern. Now, again, I said we would have the same standard to decide whether we have linear correlation or not, and that's going to be through a table which is in our formulas packet, which I've attached to our Canvas documents for the week that we're on. It's table A6, and it is specifically to decide if R gives us evidence that there is a linear relationship between X and Y, or whether we do not have enough evidence that there is a linear relationship. So we're going to say that there is linear correlation, and it's missing the title here, linear. It really should say linear correlation. There is linear correlation if the magnitude or the absolute value of R, what we calculated, if it is at least the critical value listed on the table. And we say that there is no evidence of linear correlation if the magnitude or absolute value of our calculated R falls below the critical value on that table. So here's a little snippet of that table, table A6. It does go a lot further down, but I cut it so that I could magnify it and make it easier to read. In this table, we're going to find the correct sample size. In this example, we had 9 ordered pairs, so our sample size is 9. And using a significance level of 0.05, the critical value is 0.666. So that is what we're going to compare the R value that we found against. So you might remember that we had a value equal to 0.947. 0.947. Well, here's our critical value, 0.666. 0.947 is clearly, let me move this out of the way, 0.947 is clearly above that value, right? So it falls into the significant region. That means that we do have evidence that there is linear correlation. If the R value that we had calculated fell somewhere in here, maybe like R equals, I don't know, 0.05, it would not give us enough evidence that there is linear correlation. So in this case, we claim victory and we say that we do have evidence of linear correlation because the calculated R value is beyond where the critical value is. So this slide pretty much repeats what I just said. We say that there's correlation if the calculated R value has a magnitude at least as great as the critical value on the table, and that there's no correlation if our computation for R has us with a magnitude less than that critical value. If we translate that into English, because we're talking about the Powerball jackpot amounts and the number of tickets sold, we say that there is evidence that there's a linear correlation between the amount of the jackpot and the number of tickets sold. And if you know anything about how lotteries work, this makes sense. The more tickets that are sold, the higher the jackpot amount that could be awarded. So in real world application, that linear relationship does make sense. And here is a more thorough interpretation of this example. The higher ticket sales do tend to go with higher jackpot amounts. However, just because we found evidence that there's a linear relationship between these two variables, we need to be very, very careful not to use the word cause. There is no causation necessarily, even if we find correlation. So we're going to have this as another item to look out for in a future slide, but you may have seen this on posters or even memes. Causation does not come from correlation. Correlation does not mean causation. They're not synonymous and they cannot be used interchangeably. We're also going to look at a different calculation, the value of R squared. So if we were to square the linear correlation coefficient R, it gives us another value that we use to interpret. It's called the coefficient of variation. Coefficient of variation is R squared, and it explains a little bit more about what the linear relationship between X and Y can be attributed to. So with our example where R was 0.947, we find that R squared is 0.897, and here's how we interpret that number. We say that about 90% of the variation in the ticket sales can be explained by the linear relationship between the jackpot amounts and the number of tickets sold. In other words, about 90% of the fluctuation in those values can be explained by the relationship between the two variables. That means that another 10% of the variation has to be attributed to other factors.